Welcome to the third talk today in the morning by Francesco Vaccarino. He's talking to us about parallel decomposition of persistent modules through interval basis. Please, Francesco, take over.
Thank you. So, first of all, hi everyone, and a big thanks to the organizer, both for organizing this event, which is so far, until I will start my talk, very interesting, and also for inviting me. Thank you. So today I'm going to talk to a recent work we put on archives a couple of months ago, together with these people listed there: Alessandro De Gregorio, Marco Guerra, Sara Scaramuccia, and myself. And Alessandro has just defended his thesis, his PhD thesis. Marco is going to do next year. And Sara actually is a postdoc in my group in Torino. So thanks to the co-operator for their work. The theme of this talk and of our paper is this one. So here, I know maybe you laugh because this talk has been, as this introductory part, I assume everyone knows this, but anyway. So as you know, many people, although this workshop is beyond persistence, but we think that at the moment there are something that might be interesting still to do on classical persistence module and related stuff. So in particular, as you know, roughly speaking, the framework of simplicial homology, persistent simplicial homology, is to provide a filtration of simplicial complexes and associate to that sequence of diagram, or as we will call a persistent module, made by their homology groups. And using this concept, this is the general concept, and this is the kind of things we are working on. You can think for a while about persistent modules. We restrict ourselves to sequences of finite dimensional vector spaces over a field, and also to the case where this number of steps is finite and the last map is 0. So everything will be killed at the end. The main theorem on this stuff is a rather classical one. I mean, it's an adaptation of a classical decomposition of a module over principal idea and domain, and is the graded version. And practically is telling us that if you consider the direct sum of this module Mi, these vector spaces, you have very easily, by using the structure map, the phi I here, this map, you have induced on this direct sum the structure of graded modules, so you over the ring of polynomial in one variable. You can see it this way, but you can also see it if you like to use as an example quivers, as Vidit talked yesterday. You can see this as a representation of a quiver of type AN, or another way is to see it as a module over the incidence algebra of a totally ordered set. Okay, so you can represent it in many ways, but this is the most common. And practically, as you probably all know, here you have this notation, which simply means shift in the degree, which stands for the point where in the filtration something is born, and then you have depth, so you see where generators disappear, objects disappear in that stuff. So practically, this is the composition of our persistent module into cyclic subgroup. This part here are, sorry, this is too big. Okay, this and this. This is the torsion part with finite cyclic group, and this is the free part with elements of infinite order. Okay. Okay. So the question is that practically we have that our persistent module should only contain term of this form, where I is something to denote exactly those cyclic subgroup in which D might be finite integers or infinite. Okay, this corresponds, as you know, as barcode and so on. So this is the interval decomposition, and some of them might be repeated and so on. So what we are interested in is to find homogeneous generators of these of cyclic submodule of M, such that M can be written in this way, where I of V is the submodule generated by a single element. Okay, so there are several algorithms. This is that do something like this, or at least find a set of generators. This is one of the maybe the most known is the due to Zomorodian and Carson, 2005. And the idea, and I give you now an example, the idea is to consider a sequence of simplices as they enter in the filtration, and write down a boundary matrix where the hive column of this is the boundary of the simplex. Now everything will be written over Z2 for simplicity, okay? So there's only 0 and 1, okay? What in the example I'm going to show. And then you can reduce the matrix D in such a way R can be written as D times V, where V is an upper triangular matrix, okay? Practically, you use something that we, sorry, one second of pause, because there is a terrible noise outside. Wait. Forgive me, please. I have forgotten to close the window. And okay. So practically, this is a standard thing that we taught in a course in the first year of university in linear algebra. So it's a reduction by elementary rows or columns operators. It depends what you want. In this case, by columns. So just to give an example, imagine here we have two steps, and the blank part of the matrix means everything is 0. Here you can see as an example that just to see, we have as an example 0, 2, which is in the first step, and this is the boundary, okay? 0 and 2, okay? So this is the matrix to be, from which we generate the matrix R by reduction. Practically, the matrix R becomes this one. And simply this is a matrix which is reduced by column. And this is V. This is the matrix such that D times V is R. And practically you see that the column here, 0, 2, and 2, 3 are those one giving us the generators of the persistence homology module in this case. So you see here, again, repeated the various guys all together, okay? So this is D, this is V, but if you see D and R, exactly, you get the columns that we need, okay? So what is the point of this? It's okay, it's providing you generators, but the point is that these generators in general are not the one that we need. They do not correspond to the decomposition in interval, okay? We see it here in this case. You see H1 of K0, this is the map before. And if H1 is 1, 2 plus 0, 1 plus 0, 2 is one cycle, and the other is 1, 2 plus 1, 3 plus 2, 3. It turns out that H1 of K0 is generated by H1 of 2 linearly, and H1 of K1 is generated by H, where H is the common image of H1 and H2. So the submodule generated by H1 is not in direct sum with H2. This is the point. Okay, so graphically is this. If you take the half torus, you have the two cycle. Let me call this is let me say H1 and this is H2. And what happened is that along the filtration they collide, but the module generated are done this way. The two modules glue together. What you would like to have is something not like this, but so the point is that along the steps, you find the linear generators so that the two modules, as an example, become equivalent to H1 is equal to a linear combination with the other, etc., etc. So practically what we would like to have is something like this. So we would like to find a basis such that the two cycles do not mix up, but survive along the various steps. Okay. Okay, so practically an interval basis given a persistent module. Notice the persistent module, we mean again something like a family of vector spaces with maps and so on. We are not talking about homology for the moment. Homology was the motivation, but now we are stick on persistent module, and practically persistent module we call an interval basis, a subset of homogeneous element. If and only if M can be written as the sum of the cyclic group generated by the element in the basis. Okay, so this is our objective. We want to try to see if it is possible, and we show how, build such a thing. And then we will apply the found algorithm. Can be applied to homology, okay? But in the special case, when the base field is R, we take advantage of the Hodge decomposition induced by the Laplacian operator, and we use it to compute homology in an interesting way based on harmonics. So let's go on and see what happened. So this is the repetition of what I have said so far. Okay, so I repeat, we want to do this. Practically, we don't want to have that thing, but I think here there is a mistake in the diagram. Yes, because this way makes no sense. Yeah, I will check it after. I see there is a mistake there. In any case, the main idea here, the basic ingredient, is to use this situation to consider a flag of vector spaces. Okay, this flag of vector spaces is obtained by composing maps, and we want to use build a basis of MI adapted to the flag. If for every vector there is an index such that you obtain this fact that until a certain step is not zero and then becomes zero. Okay. Any questions so far? So if some of you already have seen or read in a paper, I don't remember if it is 2008 or 2010, which is Zigzag Persistence by Carlson and Silva, they have a similar strategy in building this kind of compatible basis for IN type module. But the great difference is that their filtration is built by composition of the map. Okay, so you take instead of doing this, you do something like this. Imagine you have, as an example, fixed MI and all the previous one, and so you do something like this. And this is just to say phi I minus 1. What you do is to do this in the other case. How to do this? Wait, on the page. Okay. Okay. So in this case, the idea is the following: you have this MI, and they here consider the images of the composition of all the previous map. Okay. So here, practically, you take, if the map pointing here is denoted by phi I minus 1, you will have phi I minus 1, phi I minus 2, blah, 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 phi 0 of M0. And then this guy, as an example, is phi I minus 1 of Mi minus 1. So using this, they build a filtration they call RIR in this way, and they work on this data. And in particular, they work on Ri divided by Ri minus 1, so the co-kernel of these maps. On the opposite, we work with kernel, and we will see that this makes the things easier to deal with. Okay, so let's go back. We have this. And so the idea is this: the input, you have a sequence of matrices of maps as you like. You take bases which are given. So as an example, imagine you are working with a module, so it's given by basis of the vector spaces and the matrices with respect to those bases. And for each step MI of the persistent module, we compute an adapted basis and take the vector independent from the previous image. This is the strategy. So we practically build the map step by step by adding pieces. And so first step, you compute an adapted basis of M0, and you add all the vector to the set, the empty set, because there's nothing before. Record for each vector is index, so the number for which it holds that the map is different from 0 before and then becomes 0. So it's lifespan. So first step, you compute an arbitrary basis and compute the lifespan of each element in the basis. Practically, this corresponds to a point in the barcode of the persistent diagram having first coordinate 0 and the second one equal to 1. So far, nothing strange. Then you compute an adapted basis of MI. There is an algorithm to do that. It's not difficult. Practically, you know, you do it again by Gaussian, by elimination. And then you do what? You compute an image, the basis of the image of the previous map. So you have Mi minus 1, which is mapping here. And here is Mi. And here you compute U, the basis of the image. This is the image. Okay. And then you complete this by adding vector from the list you have found before, this list, in order given by their indices. So you order this guy according to their indices. So you have let me call this for a moment, Si1 is less or equal than Si2 is less or equal than Si Ki. So the index practically in algebraic term is the order of the subgroup generated by this guy, starting from that point. So then what you do, you practically have a vector coming from the past here, and vector that are new, okay? And what you do, you add the vector used to complete the basis to the set V and save their indices. This is the information you retain. So imagine step by step, you compute the image of the map and you add, you complete the basis by adding element of the adapted basis of the corresponding point. Okay, so this is the mechanism in practically. And this is the description with a little bit more information. So adapted basis, indexes, reduce, and then you consider V union the one that you have preserved, that you have retained. Okay, so this is the game. And so practically what you have that your interval group are going on independently in this way. Then you have added a new element here, and you have added the one with a shorter lifespan. And then you go on with this. This is an example. This is an example very, very simple, but illustrative. Imagine this, you have phi 0 is not, just to have some support. So you have an adapted basis of R is everything, because after you compose all the map, you get 0. And the image is 0. Then V for the moment is 1, M1 from here. Then these are the maps. And the second step, an adapted basis given by 1 minus 1 and 1, 1. The image of phi1 is 1, 0. And then we add the 2V, this vector, which at this point will have persistent pair to 4. And the last passage, there's nothing, so we add nothing. Let me give, wait a second, please. Okay. Let me give now another example. Again, trivial, but just to show the mechanism. So practically here, you have the mapping are practically simply the, so people, this is what we are aiming to. So we want to obtain something like this, starting from mapping that are not in this shape. Clearly, it will not exactly this way. There might be a sort of steps form of the matrix, but what we would like to have is something like, here we have a block like this and the remaining is 0. So we want to inject things and add things that not arriving from the previous one. So in this case, doing the same game I have described before, this is where the element lie, let me say, where the homogeneity of the element or the step in the filtration, if you like. And this is an interval basis in the sense that the sum of M1, M2, M3, M4, M5 as a module over the ring of polynomial will decompose in the intervals generated subgroup, submodule generated by these elements. And this is clearly somehow obvious, no? Because you see, practically you have in M1, you have these two guys, okay, that repeat here. And then you add this. And so on. And then you add this. And then you add, sorry, these are the maps. I'm writing bad. Okay, this is R3. Okay, this one, and then this one, and then you add this one, and then you add this one, and so on. So here more or less is the same, but with random number, but as you can see, again, it produces this kind of sequences of vectors. The key point is that these guys are generators of the persistent module as they are usually found by the classical algorithm. But the extra feature is that they exactly generate the interval module in which is decomposed the module. Okay, so this is the objective. So let me go back to here. one point is that you can always, it's not difficult to show that for every MI, you can build an adapted basis constructed such that the first part of the basis is a basis of the image, okay, of the previous map. This is not difficult to show, is a lemma. And so we practically define VI birth as the remaining. Okay, so you have VI written as image of phi minus 1 union VI birth. And essentially, the union of these guys is giving you the set of generators of the decomposition. The indexes give a function that give us practically come si dice? Yes, you can use the indexes to order them, and you take any non-decreasing function is working. Okay, so practically the key point of the game, but I will not give the proof, is some tedious but not very complicated computation. First of all, the first point is that for any I less than j, the map phi jt restriction of the map phi j to the subspace generated by those vectors in VI was index is more than j is an injection. So it means that these vectors remain independent from the structure. They cannot be written as a linear combination along the module. Okay, they maintain this kind of shape that we see here. They go on this way. They simply go on at certain point die if they die. And the second point is that for any I less than j, phi j, the image of the intersection of new vectors intersection with those one in the image is always 0. So the image of the linear span of two subsets are always in direct sum. So this means practically that you get the decomposition. These were some examples. And here something strange happened. What is this? Okay, delete. Okay, so there was something in the slide. So any questions so far? Is it clear, the mechanism? Okay. So now what happened? So the Hodge Laplacian has been introduced several times in the previous talks, also yesterday. And I don't think we need to spend a lot of word on this. It's simply a definition. It has many properties, can be interpreted in many ways, message passing, and so on. The key point for us is about the case when the ring of coefficient we are working on is the real number, okay? Or, yes, a real number. The point is that in this case, I write it here. I jumped a slide. Sorry, sometimes I'm quite messy. On the page, okay, nice. Okay. So as you have seen before, practically you have that under the Hodge Laplacian, you can decompose, as an example, the chain group of a simplicial complex as HK plus BK plus, let me call this the image of delta KT. Yes, Bordi cobordi. Yes. Yes. Okay. This guy here is the kernel of the Laplacian, and it's also called harmonics. We have here Professor Jost, which is a master in this thing. And what I'm interested in is to take advantage of this Hodge decomposition, which is based on many simple property really of linear operator such that the composition is 0, but in this case we are interested in boundary, co-boundary. So what I'm interested in is the fact that the Cave homology group is isomorphic to HK. So practically, what we want to do now is to take our algorithm and we want to use it to a persistent module which instead of using factoriality and so on, so things like this, so instead of using the classical approach that one has with taking advantage of factoriality of the homology, with some simple computation that I will show, it is possible to do something like this also for harmonics. So we will see that there is a map here induced by the map here, where F is the map from Ci to Ci plus 1. And we build a persistent module made of harmonics, and then we use the algorithm to find the generator of the decomposition, and this will give us an alternative way of computing persistent homology of the filtration. Okay. So the idea is here. If you consider a chain map, practically you can use the decomposition that I showed you before, because that decomposition I didn't mention, but is an orthogonal one. I mean, all spaces here in the direct sum are orthogonal complement to the other, so you can do this as an example. And this is orthogonal to HK and so on. And using this, you can consider the orthogonal projection. And so you can take a composition of these maps in this way. You have, here is the isomorphism between harmonics and homology group. This is the map induced by the homology factor. And this is, again, the same isomorphism, but on another point. And this map is written here. So this map is simply given by considering materially, you consider the inclusion, AK in CK, then you consider the FK, from FK you do DK, and here you consider pi K D to be precise, and you project on IKD. Okay, so you have this decomposition. Okay. So practically, what we have is that if we have the harmonics computed on a filtration together with these maps that I have just described, this is a persistence module. And we can apply our algorithm to this case to compute the interval decomposition. One question that may pop up is that why? So what is the advantage of doing this? The advantage is that you can do this distributed. You compute separately all the maps that you see here around. You distribute on many computers, and they use the algorithm for interval basis to reconciliate the data produced by this distributed computational homology. As an example here, you can compute the homology and this decomposition. As an example, this decomposition, where is it gone? Here, okay, here is okay. So as an example here, you can decompose the map in this way, and then use over R SVD to compute the various map involved in the reconciliation. But also, as an example, you can apply this in this case by taking simply the kernel of the Laplacian. You compute the kernel and then you compute the projection. You can use as an example Penrose pseudo-inverse or whatever, it depends on the situation. So this is a standard linear algebra. So practically you can, given filtration as an example, you can compute persistent homology by fully distributing the computation around. The reconciliation is based on that algorithm, which is at the very end some row reduction. And if you are on SVD, you can take advantage of, sorry, if you are over R, you can take advantage of SVD. So the conclusion, more or less, about these things are that we have a new algorithm for computing persistent from persistent module rather than filter the chain complex. So if you have a module with map, you can compute the decomposition. It is obviously applicable not only to persistent modules made by homology groups, is not necessary to, as an example, I give you this. Imagine you have a sequence of simplicial complex which is not a filtration in the sense that the map are not injected. Okay? You can nevertheless compute in each point of the filtration the homology group, as an example, by using the Edels-Brunner algorithm. And then it's not difficult again to write down the map between the corresponding chain groups, because I mean, it's trivial. You have the basis of simplices, you write where the simplices go. So some of them maybe go zero because they glue or disappear, okay? So are not injective. With this ingredient, I can build using over R as an example, I can use the harmonics and I can build the persistent module even in the case in which you have not a filtration but maps that are not necessarily inclusion or injective. You can distribute the implementation, as I already say, and the version over R take advantage of the SVD classification as well as the use of the harmonics, as I told you. There might be some numerical issue with SVD because there, I have to take, would like to thank Nelson, I don't know if he's here, because I already given this talk more or less some weeks ago, and he pointed out that there are some problem in numerical stability in SVD. But since then, we have made our own work and we see that it's possible to probably overcome this issue by using QR factorization instead of SVD factorization. And this is the point. So practically, I don't have much to add. Maybe I'm finishing early, I'm sorry. But I hope that the message pass, and it is that it's possible to compute persistence on general persistent module of type AN. This is AN. We didn't work with general quivers. There are some work, recent work of Carson, which is here, I think. Where is gone? Yes, here, where they introduced some consideration on using also general quiver, but they start with N. I have to also point out that in this work of Carson and Dvaraknath and Nelson, they had have a different approach because they practically are very interested in finding way to build a special basis. In our case, let me say, so to find the generators in our cases, the approach is somehow awkward. We start in finding the basis and then we find the generator as a result. Okay? So this algorithm consented, which is not so complicated, consent to find the decomposition, the generator of the decomposition, the barcode for a general persistent module supported by IM quiver type. And the difference also with respect to the old work by on Zigzag by Carson and De Silva is that there is not really clear which are the generator, and also the fact that they use a different approach based on co-kernel and filtration of composition of maps. I don't want to bother you further. I think that that's all. Probably we will try to adapt these to the general IM case in which the arrow may be reversed. We have to check about this. But for now is what we have done so far. Thank you for your attention.
Thank you very much, Francesco, for your wonderful talk. As usual, please send a Q in the chat and I call you up for a question. But let me use my privileged situation right now and ask the first question. Is there also a connection between your algorithm and the spectral sequence approach that allows distributed computing of persistence?
The truth, I don't know. I have to think about this. I don't know. I didn't think about that. I don't know. But I work it here, suspect. Okay. I don't know. It is a recent work we have done in a few months, and somehow there are still aspects to be considered, and I surely will go through this, but I don't know what to say.
And one thing that struck me, you mentioned that your algorithm can also be used when you don't have inclusions, but rather simplicial maps, or maybe not even simplicial maps because you do it on the homology level.
Yeah, because
how does it compare? So there are algorithms that people suggested for simplicial maps, but there's usually computational overhead.
I mean,
do you know anything about the comparison in terms of running time?
I think that we didn't perform a comparison, but we will do for sure, because the next step in this project is clearly to let me say produce some. I mean, formally everything is correct. Okay, now I mean we hope so. We send it is under review at the moment. Okay, but clearly there are things to do. So more comparison with other diverse approach, because we compared only with those one working with generators and decomposition and so on, and the other one is to check it with some benchmark. This is one problem. What are the topological benchmark? But in any case, to test it somewhere against other things. Here, for sure, this work for simplicial maps, because there's no requirement on the linear map between the modules as in persistence. But since the algorithm do not rely on looking, to destroyer generators, the work done by simplicists and the filtration, there's nothing on that. It's purely algebraic. It clearly can be applied to general mapping between simplicial contexts. There's no use of the simplicial information in this game.
I see Wojciech has a question.
Non hai il microfono, Wojciech.
Right. No, so my question is about, so your algorithm works on, on the parameterized vector space, not on the, like, for example, Ripser, right? The input for Ripser, you need to give, well, maybe a distance space, and it converts, to Vietoris Rips, and then calculates homology and barcodes. Now, your input is actually parameterized vector space, or am I wrong?
The input is, yes, call it as you like. I mean, a persistent vector space, or a graded vector space.
Exactly, a persistent vector space. But you see what's,
yeah,
I mean, yeah. So for example,
go.
Yeah, diagram of vector spaces.
Yeah.
But for example, but that's quite hard, right? To get from simplicial complex or a functor of simplicial complex into a functor of vector spaces. That's typically an expensive step. It's not actually. It's not,
mm-hmm. But I didn't understand what is the question.
No, I'm just trying to sort of, I'm making a comment that typically an expensive step is to get from, functor of simplicial complexes into these parameterized vector spaces. Actually taking the homology, right?
Yes, but the point is this. Usually what you have now, typically you have something like this. Now you have a filtration. This is the standard setting. Now you have a filtration induced by some parameter. If it is ellipse vectoris, it's the distance or whatever it is, doesn't matter, okay? You have some filtration. Attached to this, you have the corresponding chain groups of a certain size. And then you can build this guy with the operator. This is expensive. This is the expensive, okay? Because although it's local and it's very sparse, you have to check a long list of things. Imagine you have the simplest case. You have a vectoris ellipse, which is a flat complex. It's completely encoded by.
Absolutely, that's expensive. Exactly.
And you have to produce the boundary matrices. This is a pain in the ass, okay? Okay, but. This is always this. I mean, if you have data, you want to represent them in another universe, as we do usually. You always have to pay the due at a certain point of encoding your data in terms of filtration or whatever. That's the point.
Yep.
So at the end of the pipeline, you might have abstractly, you might have something like this. You have a single parameter, fully ordered set. So practically, you have a functor from the totally ordered set of order n to this. Practically, maybe it's better to put this n only, okay? Sure. Because it's not, okay, it's not subsets. Okay, you have a map like this usually, and this is persistence more or less. So here you can have a category if you want to be fancy, put anything where it makes sense to do. It is clear that if you, building these spaces may have a low cost. As an example, chain groups. This is costless because your data is the filtration and the list of generator is standard, is simply the list of stuff you have. And then the filtration case is easy because you always have matrices like this, no? You have matrices like 1, 1, 1, 1. So here you have some identity and the remaining is, and here you have a lot of zero, okay? This is when you have filtration, the map between the chain group are trivial somehow. But meaning the map can be more complicated means that the map are given somehow. I'm not concerned about how the map are built. I'm assuming that the map are built in some way. But at the end of the game, the things we are dealing with is something like this. We have a list of vector spaces with maps.
Sure.
At least
no, Francesco, I agree. But what I would like to point out is that, for example, Ripster doesn't store these chain complexes for which we get, right? Because that's an expensive one. To going from chain complexes to its homology. This is also an expensive part. Of course, the second part, that what you've presented, also is costly. But there is this other, to get there's this other ingredient that's also costly, right?
Yeah, I understood what you mean. Okay. You mean okay. You when you compute persistence with so-called classical algorithm, you produce in one shot persistence and homology. Somehow, exactly. Okay, from the boundary. Here I need to compute homology, and then I compute persistence by using my algorithm. The point is that this is not sequential. So you can distribute. We have cloud computing. So one thing you can do, as an example, we will do, you can even do with virtual core. You can put the computation of the various homology group around in the cloud space, and then reconciliate this instead of waiting and waiting that step by step you are doing everything. This is the advantage, in my opinion. And yes, this is what.
Thank you.
No, I'll explain you why. Because when you made these things on a scaffold in the past, using the Tamal-Day algorithm, one of the big problems in computing persistence and so on is that very often the final steps are super heavy because you have gigantic homology spaces, or chain groups, so the matrices becomes enormous, no? Usually when you have a filtration. So imagine you can distribute this. So you put in one side the big one and all the small one, blah, blah, blah. And the total time you need is less than doing in sequence. I'm sure of this. That's the spirit of this, distributing persistence. Sorry. Okay. I'm not too late.
Thank you very much, Francesco.